Hi students, welcome back to the new session. In this session, we are going to discuss about factors influencing or affecting ionization energy. So this is a very important board examination point of view question. Even this is also important for intermediate. That is, you will get this chapter in intermediate first year. So there also it is a very important question. In 10th class also it is a very important question. Sometimes it will be given in 4 marks or in even in 6 marks. If it is missing there, chance of getting even bit part also. So we'll discuss what is ionization energy and what are the factors influencing or affecting ionization energy. Now let us discuss first what is ionization energy or ionization potential. Ionization energy or ionization potential. It is the minimum amount of energy required. I will write the definition. It is the minimum amount of energy required to remove an electron from a neutral isolated gaseous atom is called ionization energy or nothing but a potential. Okay, so the units of ionization energy are electron volt per atom, electron volt per atom, or kilocalorie per mole, or kilojoule per mole. Even you can write this one as kilocalorie mole inverse or kilojoule mole inverse. So these are the units of ionization energy. So it is the minimum amount of energy required to remove an electron from a neutral isolated gaseous atom is called as a ionization energy. So units are electron volt per atom or kilocalorie per mole, kilojoule per mole inverse, kilojoule mole inverse or kilojoule per mole, kilojoule mole inverse. Kilocalorie mole inverse, kilojoule per mole, kilojoule mole inverse. So these are the units of ionization energy. Now this ionization energy is of different types, and we are having a first ionization energy, second ionization energy. If you go on writing, we can go with the even third ionization energy also. What is the meaning of this ionization energy? Basically here we are discussing about two types. First ionization energy, that is IE1, and second ionization energy IE2. What is first ionization energy? It is the amount of energy required to remove the first electron from a neutral gaseous atom or neutral isolated gaseous atom. It is the amount of energy required or minimum amount of energy required to remove an electron, to remove the first electron from an isolated gaseous atom is called as a first ionization energy. For example, I am considering M is an atom. It is a gaseous atom. So I am going to remove the first electron. If I remove the first electron, very clearly I am first electron, it is going to convert into gaseous ion. So it is the minimum amount of energy required to remove the first electron from a isolated gaseous atom or neutral isolated gaseous atom to convert into a gaseous ion is called as a first ionization energy. Now what is the meaning of this? Is nothing but a IE1. IE1. Sir, what is IE2? So it is the amount of energy required to remove the second electron from this zone. You consider M is some element, it is a gaseous, very clearly, and this is a gaseous ion. So it is the amount of energy required to remove the second electron. I am writing very clearly second electron from a gaseous ion or uni-positive ion to convert into a di-positive gaseous ion is called as second ionization energy. I am going to remove the second electron from a gaseous ion, uni-positive gaseous ion Okay, to convert into di-positive gaseous ion, I am going to remove the second electron. If I remove the second electron, it is called as second ionization energy. So among these two ionization energies, IE1 is more or IE2 is more means IE2 is more. So ionization energy IE1 is less than IE2 or IE2 is greater than IE1. Sir, why sir? As electron is removed, the amount of charge on the respective ion is increasing, thereby attractive force increases, then you require more amount of energy to remove the electron. Okay, so this will be clearly explained in intermediate level, but in 10th level it does not require much about it. Just for simple knowledge sake, understanding purpose only I mentioned these two clearly. So now we will discuss about what are the factors affecting ionization energy. So in these factors, okay, the different factors are affecting ionization energy. The factors are, first I am writing atomic size. Okay, atomic size. What is this? How this atomic size will affect the ionization energy? So as atomic size is increasing, okay, atomic size. First factor is atomic size. As atomic size is increasing, ionization energy decreases. I will give two examples for ease understanding purpose. Okay, as atomic size is increasing, as atomic size, I will write simply atomic size is inversely proportional to ionization energy. In the sense, as atomic size is increasing, ionization energy decreases inversely in the sense one is increasing, the other one will decrease. As atomic size is increasing, ionization energy decreases. As atomic size is decreasing, ionization energy will increase. Okay. For example, sir, can you give an example for this? Okay. I will go the elements which comes under first group and second period. Okay. Now, take the example. First group elements hydrogen, lithium, sodium, potassium, rubidium, cesium and francium. And second period elements lithium, beryllium, we have boron, carbon, nitrogen, oxygen, fluorine, neon. So among hydrogen and lithium, now I will explain with this one with a very clear explanation. Hydrogen atomic number is 1, lithium atomic number is 3. Hydrogen contains 1 electron and lithium contains 3 electrons, 1 proton and 3 protons are there. Okay. For next, I will draw electrons in the orbit level or shell level. 1 electron is there. Here nucleus is having 1 positive charge. We know that because 1 proton is there. And lithium, in case of lithium, 3 protons are there. First shell 2 electrons, second shell 1 electron. See, in case of hydrogen, the only one atomic number is 1, only 1 electron is there. That electron comes under first shell. In case of lithium, we have atomic number 3, 3 electrons are there. First shell, we know maximum 2 electrons and 1 more electron comes under second shell. So the number of shells are more in lithium compared with the hydrogen. So as you see here, the electron comes under first shell, which is very much closer to the nucleus, more attractive force. So here in case of lithium, the last electron comes under second shell. The distance from the nucleus is increasing, so attractive force decreases. Thereby, we can able to remove the electron more easily here compared with this hydrogen case. Lithium, the electron present in the last shell of lithium can be removed very easily compared with the electron present in the first shell of a hydrogen. So as atomic radius is more, atomic size is more, the size is less, here is more, and if you go to sodium, the last electron comes under third shell. So the size further increases. So as atomic size is increasing, ionization energy decreasing. If I talk about a period, in period left to right, you know atomic radius, atomic size, atomic radius decreases. Hence ionization energy will increase. Understood? So as first factor, as atomic size is increasing, ionization energy decreases. As atomic size is decreasing, ionization energy increases. We can write simply inversely. Means if this is increasing, this will decrease. If this is decreasing, this will increase. Next factor which we are going to discuss, the next factor is after this, the next factor is nuclear charge. Nuclear charge. Next one is nuclear charge. As nuclear charge is increasing, ionization energy increases. Sir, explain. Very clearly means I will explain now. Nuclear charge is directly proportional to ionization energy. So directly, as the nuclear charge is increasing, ionization energy will increase. Okay. Now, listen. For example, I will go to the example of lithium and beryllium. Lithium and beryllium. Lithium atomic number is 3, beryllium is 4. Okay, lithium atomic number 3, configuration is 1s2, 2s1. Okay, and nucleus contains 3 protons. Outside the nucleus, we have 3 electrons. Okay, if I write this is a nucleus, 3 protons are there, 3 positive charges are there. First shell 2 electrons, second shell 1 electron. Okay, now in case of beryllium, atomic number is 4, configuration is 1s2, 2s2. It contains 4 electrons and 4 protons. So, if I write very clearly about this, nucleus of beryllium has got 4 protons, 4 positives. Outside the nucleus 2 electrons and here 2 electrons. So, the nuclear charge here is plus 3, whereas the nuclear charge here is plus 4. Plus 4 charge, second shell 2 electrons, towards the nucleus more attractive force compared with this lithium. Lithium nuclear charge is plus 3 and the first shell 2 electrons, second shell 1 electron. There is a attractive force between these two also, but here the attractive force is more towards the nucleus because nuclear charge is more. So hence, as the nuclear charge is increasing, ionization energy also increases. Nucleus with more charge will have an ability to attract the electrons towards it with a higher attractive force. So hence it is very difficult to remove the electron. So here it is very difficult to remove the electron compared to this case. And one more we can connect here. Size. Lithium is having a more size than that of beryllium because in periods left to right, atomic radius or atomic size decreases. Hence attractive force is more. So more energy you require to remove the electron because the nuclear charge is more. Here is lithium is plus 3, beryllium is plus 4. Hence nuclear charge is more for beryllium compared to the lithium. Attractive force is more towards it. Hence you require more energy for beryllium to remove the electron compared with the lithium. Okay. Next one, the other factor is we'll be talking about penetration power. Penetration power. Excuse me. Penetration power. As the penetration power is increasing, ionization energy also increases. Penetration power is directly proportional to ionization energy, sir. What is the meaning of this, sir? We are not understanding. Penetration power in the sense the ability of an electron to enter into a given energy level, shell or subshell. Okay, maybe it is the orbital. For example, if I explain an example, then only you will understand this particular factor. Okay. Now, hydrogen you take the best example, go with the element like neon, best example. You can go a number of examples. Okay, with a number of examples. Neon atomic number is 10, contains 10 electrons, 10 protons. We least bother about protons here in this case. We'll be bothering about electrons. Okay, configuration, if I write the neon electronic configuration 1s2, 2s2, 2p6. You tell me, according to above principle, electrons always occupies the orbitals having least energy first. So among all these three orbitals 1s, 2s and 2p, electron first enters into 1s, then only enters into 2s, then only into 2p. So electron has got an ability to enter into 1s first, then only into 2s, then only into 2p. So as electron is entering first into 1s level, so you require much energy to remove the electron present in the 1s level. Okay, because it is much closer to the nucleus. If I show very clearly, this is the nucleus, first shell, K shell, N is equal to 1. This is N is equal to 2, L shell. Now 1s comes under this 1s2. Here is 2s2, 2p6. So among, if you observe all these three, First electron enters into 1s orbital. 1s. So as electron is entering into 1s first, so you require much energy to remove the electron present in the 1s compared to the 2s and 2p. So penetration power is more for 1s. Penetration power of 1s is more than 2s. So penetration power of 2s is more than 2p. Okay. So 1s is having more penetration power than 2s. 2s is having more penetration power than 2p. Understood? So among all these three orbitals, if you take, penetration power is more for 1s. So you require much energy to remove the electron present in the 1s level compared with the 2s. You require more energy, more ionization energy for 2s, electron present in the 2s to remove than that of 2p. So by this we can understand that as penetration power, the ability of an electron to enter, to go into a respective orbital or subshell. Okay, so based on that, if you consider as the penetration power is more, ionization energy also increases. So among all these three orbitals, okay, for which orbital you require much ionization energy to remove the electron means 1s, then only into 2s, then only 2p. So you require much ionization energy for 1s than that of 2s, than that of 2p. So as penetration power is increasing, ionization energy also increases. If I ask you one question, among, I will write one configuration. Go with the aluminium. Atomic number is 13. 1s2, 2s2, 2p6, 3s2, 3p1 is the configuration. Among all these three orbitals, all these are orbitals according to the configuration, which orbital require much energy to remove the electron. Okay, to remove the electron from which orbital you require more ionization energy means 1s. Least is 3p. After 1s, you require little bit less energy for 2s, still less for 2p, still less for 3s, still less for 3p. Okay, I hope you all are understanding quite comfortably. Okay, next, next we have is screening and shielding effect. Screening and shielding effect. Next factor is as the screening and shielding effect is increasing, ionization energy decreases. Screening effect is inversely proportional to ionization energy. Means as a screening effect or shielding effect is increasing, ionization energy decreases. Sir, what is the meaning of this, sir? What is the meaning of screen, sir? What is the meaning of screening and shielding effect, sir? Means, for example, if I explain the example, then only you will understand. Otherwise, you cannot. Okay. Now, take the example of element like lithium and sodium. Best examples are go the potassium. Compare all these three. Lithium, atomic number is 3. Sodium is 11. Potassium is 19. If I write the configuration for 1s2, 1s2, 2s1. Here is 1s2, 2s2, 2p6, 3s1. Here it is 1s2, 2s2, 2p6, 3s2, 3p6, 4s1. Understood? So in this case, the last electron is in which shell? Second shell. In this case, the differentiating electron, last electron is in what shell? Third shell. In this case, the last electron is in which shell? Fourth shell. Now, even I will show you by drawing the shells also. Lithium, nucleus, first shell, 2 electrons, last shell, 1 electron here according to this configuration. Now, this is for lithium. Sodium, you take nucleus, first shell, 2, second shell, 8 are there, last shell, 1 electron is there, it is 3s1. Now, in case of potassium, nucleus, first shell 2, second shell 8, third shell 8, fourth shell 1. If you consider, here is K shell, L shell. Here is K, L, even M is also coming. Here it is K, L, M, N. The number of shells are more in which element? That is a potassium. So here, last electron is in fourth shell. So before the last shell or valence shell, we are having a penultimate and anti-penultimate shells. Inner shells total how many are there here? 3 are there. So these 3 shells acts like screens. Okay, they are acting like screens. They are giving protection. Okay, from the attractive force of the last shell electron towards the nucleus. So they does not allow this electron to be attracted by the nucleus more easily. They are acting like screens. So you require less amount of energy to remove the electron here. Because in case of sodium, we have only 2 shells are there between the nucleus and the last shell. Less number of screens, less screening effect, less shielding effect. Less screening and shielding effect, less more attractive force, more ionization energy. Here in case of lithium, last electron is in second shell, and between the last shell and the nucleus we have only one shell. So there is chance of more attractive force towards the nucleus. Hence you require more energy here. Here you require less. Here further decreases, very less compared to these 3. Among all these 3 elements, the last element like potassium is having less ionization energy because number of shells are more, which are acting like screens, which are shielding the nucleus, which are giving protection to the nucleus from the attractive force of the last shell electron and the nucleus. Okay, so by this we can understand that as the screening and shielding effect is increasing, ionization energy decreases. So among all these 3 elements, lithium is having more ionization energy compared to the sodium. Sodium is having more ionization energy than potassium. Among all these 3, least one is potassium is having less ionization energy. Next is bit more is sodium, a bit more is lithium. Understood? As the screening or shielding effect is increasing, ionization energy decreases. Next one we are going to discuss the next factor is stable electronic configuration. Next factor is stable electronic configuration. More stable the electronic configuration, more will be the ionization energy. So you know well, I think the elements with completely filled orbitals and half filled orbitals are more stable than less than half, more than half, or less than full. Okay, octet configuration, best example. I will go with the example. Stable electronic configuration. More stable the electronic configuration, more will be the ionization energy. As the stability of the atom will increase with the stable electronic configuration. For example, I will go with the 3 examples for better understanding purpose. Now, go with the element like carbon, okay, nitrogen, and even neon. Easy to understand. Carbon atomic number is 6, nitrogen is 7, neon is 10. Now we know it contains 6 electrons are there, 7 electrons are there, 10 electrons are there. Configuration, if I write 1s2, 2s2, that is 2p2, and here it is 1s2, 2s2, 2p3. Excuse me, 1s2, 2s2, 2p6. Now I will write even by using degenerate orbitals having a same energy. So that is 1s does not have any. So we are having 2 electrons with anti-parallel spins, and here you are having in P, 2px is there, 2py is there, 2pz is there. 1 electron according to Hund's rule, 1, 1. No more electron to fill here. Now here 2px1, 2py1, 2pz0, we know that. And here it is 1s2, 2 electrons, and 2s2, 2 electrons are there. And even in 2p, we are having 2px, 2py, 2pz, 1 electron, 1 electron, 1 electron, that is half filled. Degenerate orbitals are filled with 1 electron each. Okay. Next element we are having is a neon. So 1s2, 2 electrons, 2s2, 2 electrons. In P, we are having a 2px, 2py, 2pz. 6 electrons are then 1, 1, 1 based on Hund's rule. Then only the pairs. Here is 2px1, 2py1, 2pz1, 2px2, 2py2, 2pz2. Okay. So among all these three elements, you tell me which element is having octet configuration. The element with octet configuration is a neon, which is a stable configuration, fully filled orbitals are there, and the two octet configuration, because if I write clearly shell level configuration 2 comma 8, this is 2 comma 5, and this is 2 comma 4. Understood? So I will tell in terms of orbitals here. See, so in case of neon, all the degenerate orbitals are completely filled, and that too octet configuration. So elements with octet configuration, okay, are more stable. As the stability is increasing, you require more energy to remove the electron. Okay, so the ionization energy is very high in case of neon. IE is more. And nitrogen we have last shell 5 electrons are there. This is 2s2, and remaining 3 electrons 1 1 1 is filled, half filled orbitals. So fully filled orbitals are more stable compared with the half filled orbitals. So the ionization energy is little bit lesser for nitrogen compared with neon. So ionization energy of, I will write very clearly here, the ionization energy of neon here in this case, ionization energy of neon is more than ionization energy of nitrogen. And next, carbon. So we don't have any half filled orbitals, and even we don't have any fully filled orbitals. It is less than half. So we can able to remove the electron easily in carbon compared with nitrogen. Okay, we can remove the electron easily for nitrogen compared with neon. Okay, so comparatively I am telling you. So the ionization energy is less for carbon. So next after that, and carbon, we are having a ionization energy of carbon is less than that of nitrogen. Nitrogen ionization energy is less than that of neon, because neon we are having octet configuration. So by this we can understand that elements with half filled orbitals and fully filled orbitals, primarily octet configurations, are more stable. So more stable the electronic configuration, more will be the ionization energy. Okay, I hope you all are understanding my explanation. Next one is, after this we are having is a charge on the ion. Charge on the ion. So as the charge on the ion is increasing, ionization energy also increases. Charge on the ion. Charge on the ion. I will go with a very easy example. As the charge on the ion is increasing, ionization energy also increases. So ionization energy is directly proportional to charge on the ion. Nothing but, sir, which ion, sir? We will be discussing. Here it is about primarily cation, positive ion. Cation in the sense positive ion. Okay, I will go with a simple example, easy to understand. Aluminium. Aluminium atomic number is 13. Okay, aluminium I will take, Al plus 1 I will take, Al plus 2 I will take, Al plus 3 I will take. I will explain with all these four. Okay, so aluminium atomic number is 13. Configuration is 1s2, 2s2, 2p6, 3s2, 3p1. And here nucleus 13 positives are there. Outside the nucleus 2 electrons here. Second shell 8. Last shell how many? 3 electrons are there. Now here 2 electrons first shell. 2s2, 2p6, 8 electrons second shell. And here in the last shell 3s2, 3p1, 3 electrons are there. So we can able to remove the electron present in the last shell of aluminium easily, because the charge in the nucleus is plus 13 and 13 electrons are there, no charge on the aluminium atom. Understood? It does not form any ion. So you require less energy to remove the electron here in this case. So after removing one electron, now if I remove 13 electrons are there, and even the nucleus has got 13 protons are there. So it is a neutral atom, equal number of electrons and protons, neutral atom. So you require less energy to remove the electron. Okay. So next, electric neutral atom, in the sense atom is electrically neutral, that is in terms of charge, no charges on the atom. Now after removing one electron from this, if I remove one electron from aluminum, 13 is there. So if I remove one electron, it will become Al plus 1, one electron is here. So aluminum is converted into ion. Which ion? Cation with a positive charge. So nucleus has got plus 13. Outside the nucleus 2, 8, last shell only 2 electrons are there now. So we can't remove the electron more easily here compared with this one. Here we can remove the electron more easily compared with the aluminum with some charge ion. You require more energy because attractive force towards the nucleus will increase as the charge is increasing. Okay, so plus protons 13 are there and electrons only 12 are there. So more attractive force towards the nucleus. So charge on the ion is increasing, that is on the atom the charge is increasing. Now if I go with the Al plus 2, Al plus 2, it contains 13 protons and 11 electrons only. 11 electrons only. So more charge on the aluminum atom, that is cation Al plus 2, more attractive force. You require much energy. Go to the third case, Al plus 3, and even it contains 13 protons nucleus and only 10 electrons. 10 electrons, in if you write configuration for this 10 electrons, 1s2, 2s2, 2p6 na. So if you observe the configuration, this is octet large cell, octet configuration, more attractive force. So among all these four cases, ionization energy is very high for Al plus 3. Okay, is more ionization energy, having more ionization energy compared with Al plus 2, Al plus 1, then only Al. So as the charge on the ion is increasing, especially cation, ionization energy increases. Okay, so among Al plus 1, Al plus 2, Al plus 3, ionization energy required more for Al plus 3 because of already we know, I already explained octet. Next, less amount of energy for Al plus 2. Next, further decreases for Al plus 1. It is less for Al. Okay, so I hope you all understood my explanation, okay, related to factors affecting ionization energy. Okay, if you are satisfying with my explanation, please share, subscribe, okay, and like it. Please like, share and subscribe my channel. Thank you.